This oxygen is, this carbon is 0, this one is minus, this hydrogen is 0. Whereas there's only one formal charge over there. So what we have here is this screws up the formal charge distribution. And over here, this oxygen loses, this oxygen gains. So if you have a tug of war for electrons, oxygen versus oxygen, which oxygen wins? Always the top oxygen wins? Or the right oxygen wins, or the left oxygen wins? If there's a tug of war for electrons, oxygen versus oxygen, which oxygen wins? It must always be the left oxygen. The left oxygen must always win, right? The left oxygen, oh no, I'm sorry, the top oxygen. The top oxygen must always be the winner. Is that correct? Or the right oxygen? No, and so the problem is, if there's a tug of war, why does one oxygen lose and another oxygen gains? So this one is not a resonance structure. This one's quite a bit unstable. And so there are only two choices here. These two choices right here. That's it. Yeah. 34 is B. Write the electron configuration for Ag and Ag plus. What's the electron configuration for Ag? Krypton. Five S 2. 4D 9. Silver looks to be krypton 5s2 4d9. Would you agree? No? Yeah, that's good to know about, right? All right, it goes krypton 5s1 4d10. That's right. And why is that? The D subshell is only one electron short from being filled.
Wait, that's not for the ion.
This is just for the element. This is not for the ion. The ion is going to have a different electron. We need to remove one electron for the ion because it's silver plus. So what are we going to take it from? The 5s or the 4d? 5s. So silver ion is krypton 4d10. The 4d10 is relatively stable because it's a filled subshell.
So this is just one of those weird exceptions like copper.
Yeah, copper and chromium. This is a weird exception. Copper and silver are in the same family. I know you're only supposed to memorize 2. Copper and chromium. But you can't memorize everything in this world. And so based on what copper is argon 4s1 3d10. Then silver should be similar. And the same thing with chromium. If I gave you molybdenum should be similar to chromium. It's in the same family. And we've seen that pattern before. So I'll be able to extend that pattern.
Does tungsten and gold fall in the same pattern as well then?
Tungsten and gold should follow the same pattern as well. However, as you get to bigger and bigger orbitals, then there are more exceptions. There's, there are periodic tables that have there are periodic tables that have the electron configurations built in. Those are handy to have. Don't trust everything on the internet. Chromium is not 3d4, it's 3d5. So chromium and vanadium have 3d5. Copper is not 3d9, copper is 3d10. So copper and zinc are both 3d10. And so this is wrong. I'm surprised this is wrong because Wikipedia has so many people on it. I'm surprised they got it wrong. What's Wikipedia showing this for? What is that? What are these? You know what those are? Orbits. Bohr diagram? Come on. Oh, okay, this is better. Now we're starting to talk about orbitals. S orbital, p orbitals here. Okay. There are some periodic tables that do show the electron configurations, and they're correct. One of the periodic tables I just had up the other day. I don't know if we can see it because it's so small.
Yeah.
Can you? You probably can't even see it, can you? I know what I'm going to do. Although the resolution might not be so good. But do this. Although you can't see it, I'll just read it for you. Ready? Copper. They say argon 3d10 4s1. Silver, krypton 4d10 5s1. Gold, xenon 4f14 5d10 6s1. So do you see the pattern holds now? We go over here, chromium, argon 3d5 4s1, molybdenum, krypton 4d5 5s1, tungsten, xenon 4F14, 5D4, 6S2. So tungsten bucked the trend. This is from actual data. And so it almost worked for, these have worked, except down here. You know, it should be S1D10, right? S1D10, S1D10, S1D10. This is S2D9. So as these orbitals get bigger and bigger, you know, the difference in energies becomes smaller and smaller. So there's less. So sometimes we get more exceptions, sometimes we get less. But that's tungsten. See, bohrium is 5F14, 6D4, 7S2. So it reverts. You know, jump up. So the half fill, when the D subshell gets so gigantic, it doesn't make a big difference whether it's, you know, 4/10 of a slice, you know, 4/10 of a pi versus 5/10 of a pi. You know, the pi is so gigantic. You know, as the pi gets smaller, then it makes a more significant difference if there's a slice missing out of the pie. I suppose that's one way of thinking about it. But anyway, it's one of these things, you know, one of these things is that we try to use patterns to help us. You know, this is part of science. We try to use patterns to help us make predictions. Because we don't want to have to memorize everything. And so you memorize one thing and hopefully you can use that pattern to make additional predictions. Then check them. We want to verify those predictions. 39 skip, 40. 40 stoichiometry, but this is a mixture, you know, 23%. This is composition by mass, mixture, air. Sorry? Theoretical yield of what? What is the theoretical yield of heat? Theoretical yield of energy. Theoretical yield, what I mean by that is, if you burn 52 grams of methane and 710 grams of air, this is called limiting reagent problem. And so, in theory, how much heat or how much energy will be produced by burning this methane? Sometimes we use it, you know, we could use that energy for different things. You know, a lot of people call this the heat of combustion, but that heat can be used to do work as well. Or it could just be used to heat things up, like a pot of water or whatever. And so, you know, there's no actual yield, theoretical yield, percent yield. So what I'm just asking you is, what is the yield of energy? What is the yield of heat in this limiting reagent problem? 52 grams of methane is going to produce some amount of joules. 710 grams of air will produce some amount of joules. Which one is it? Well, we pick the smaller amount because the smaller amount method will give us the theoretical yield of product. And heat is a product here, or energy is a product. Now, what is heat? Heat is transfer of kinetic energy from a hot body to a cold body. That's technically what heat is.
At the bottom where it says bonus, what is LR? Thank you.
Yeah, LR is a limiting reactant. So we need to do one additional calculation to figure out how much more. Let's say if our limiting reactant were methane, how much more methane do we need to complete the reaction? Or if the limiting reactant were air, how much more air do we need to finish the reaction? So that would be a bonus calculation.
Or to 23%, because air is demanding, or could it be oxygen, helium?
No. No, I mean, air is going to have small variations in composition depending on where you're at. But typically, that 23%, what, does that number sound funny to you? 23%.
Sounds like a percent yield or.
No, that's the composition of air.
We'll just go over this one.
Let's look at the composition of air. What is the chemical composition of air? Air consists of nitrogen, oxygen, water vapor, argon, and carbon dioxide. Nitrogen, 78.084%. It's probably the average at sea level composition of air. So it's about 78% air. 78% nitrogen. But in class, I usually say it's about what?
21%.
Well, normally in class I say that air is 80% nitrogen, 20% oxygen. So I round it to the nearest 10. So 80-20 ratio. So one I'll round up, the other I'll round down. But this is not percent by mass. This is percent by volume or percent by moles or molecules. And so if I had 100 molecules of air, then 80 would be nitrogen, 20 would be oxygen. Or if I had 100 liters of air, I'd have 80 liters of nitrogen, 20 liters of oxygen. But, nitrogen and oxygen are way different amounts. So percent by mass is different. So it's about 21% oxygen, more precisely. I have it up here in one of these tabs. Composition of air by mass. So the composition of air by mole or volume is about 80-20. But by mass, take a look. Here. Goes up to about 23% oxygen versus 21% oxygen by volume, 23% by mass. So that's where I got the number for the test. 23% by mass oxygen. No. You're saying we take 710 grams of air times 100 grams of air divided by 23 grams of oxygen. Is that what you said?
Flip the oxygen in air.
Flip the oxygen in there?
Yeah.
Yeah. Then yes. If we flip this, then you're right. Because we have 23 grams of oxygen for every 100 grams of air. So if we have 710 grams of air, we can figure out how many grams of oxygen we have. And then we go from grams of oxygen to moles of oxygen, moles of oxygen to moles of, or not moles, to kilojoules. This one's a very good stoichiometry problem, but we're out of time. This stoichiometry problem, a lot of people, well, it's very good in the sense that,
there's a lot of areas for potential mistake. A lot of areas for potential mistake. Sometimes, you know, people can be shaky and still get the right answer. You know? Just barely made it through. But on that particular problem, you can't be shaky. You have to know, otherwise you get the wrong answer. 41, draw resonance forms of nitrite. Draw the hybrid. We aren't doing the hybrid. 42, draw detailed orbital energy level diagram for copper. We already did that. I did that in class. You should have that in your notes. 43, detailed wedge dash. We aren't doing that.
Well, if you have some answers you want to check, you can post it on Piazza.